Today we will talk about chemical properties of aromatic compound. What are aromatic compounds? Aromatic compounds are those compounds which have a ring-like structure with conjugated double bonds. And simultaneously, whatever the compound, if it is aromatic, it is stable. That means aromaticity is the sign of the stability. This fact will help us in understanding which type of chemical reaction this particular compound can give. Generally, we have three options of reactions in any of the compound. These are addition, elimination, and substitution. If I talk about addition reactions, in aromatic compounds, addition reaction is not possible. Why? Because if this compound will undergo the addition reaction, this will be converted into the saturated one. That means its aromaticity will get finished. That means there is no option of addition reaction. Elimination is again not possible in case of aromatic compound because it will make it more unsaturated. Elimination means saturated to unsaturated. The compound is already highly unsaturated, that means it can't give you the elimination. We are left with only option of substitution reaction. In case of substitution, again we know that there are two options. It can be nucleophilic substitution or it can be electrophilic substitution. Nucleophilic substitution means nucleophile will be substituted by the nucleophile, electrophile will be substituted by electrophile. For any compound to show the nucleophilic substitution reaction, this is needed that nucleophile should attack on this ring. One thing, the compound which is having three double bonds in conjugation, which are showing you the resonance. Actually what happens in case of benzene ring or any of the aromatic compound, there is a thick electron cloud above and below this benzene ring. That means this compound is highly electron rich, and if it is electron rich, a nucleophile, because nucleophile is coming with a negative charge, this nucleophile can't attack on this benzene ring. That means there is no option of nucleophilic substitution as well. Only one option, that is electrophilic substitution. E plus electrophile can easily attack on this benzene ring and it can replace what hydrogen present on the benzene ring easily from this aromatic compound. That's why aromatic compounds can show you the electrophilic substitution reactions very easily. How does this electrophilic substitution reactions occur? There is an aromatic compound. The most common example is benzene. What happens? Double bond shift to one position. That position get negative charge, another will get positive charge. Electrophile, which is coming with a positive charge, will attack on this side. This type of species will be formed. Hydrogen is already present there, and E, that is electrophile, which was coming there, it has taken this position. Positive charge is here. Now this positive charge will rotate via resonance in this benzene ring. Like this, positive charge on this position, then double bond is coming to this position and positive charge is here. In the final, this single bond which is in between carbon and hydrogen, this hydrogen will leave without any electron. That means leaving its two electron on this position, and the species will be created like this, and H plus is getting removed from this position. This species, if I show you the resonance, you can see that positive charge is rotating from this carbon to this carbon. This carbon is already having two bonds. Positive charge will never come on this position. This species where the positive charge is rotating from this to this is known as arenium ion complex. This was about the mechanism of the electrophilic substitution. In the simplest way, how can we show the electrophilic substitution? This is the aromatic ring. E plus is attacking on this. This type of species formed, and H plus is getting removed from this part. If I talk about electrophilic substitution reaction, it is simply the set of these 5 reactions only. Whenever you will be learning about the electrophilic substitution reactions, these reactions will be there. What are these? Halogenation, that means replacement of hydrogen with halogen. Nitration, replacement of hydrogen with NO2, nitro group. Friedel-Crafts alkylation, hydrogen by alkyl group. Friedel-Crafts acylation, hydrogen by acyl group. Last is sulfonation, that means hydrogen by SO3H group. This is electrophilic substitution reactions. Next example. In every electrophilic substitution reaction, what our target is? Our target is to create one electrophile. right? For example, if it is halogenation, what should be the electrophile? The electrophile should be X plus. X means halogen. This is called as halonium ion. I have to create X plus ion to complete my electrophilic substitution halogenation reaction. What is the thing? What is the most important thing? What is the reagent that we will use which will create a species like this? As normally we know that halogen always form X minus, but I have to create X plus. So what should we do? We will have to use a reagent which can create this X plus ion. For this purpose, we use halogen, that is X2, with AlX3. AlX3 is a type of Lewis acid. We can use even FeX3 instead of AlX3. What are Lewis acids? Lewis acids are those which can accept the lone pair of electron, or which can accept the electron pair, right? Let us see what this AlX3 will do here. If this X2 is reacting with AlX3, this AlX3, look, this is taking this electron pair which was present in between X and X like this. That means this AlX3 is accepting X minus from this X2. This will create AlX4 minus, and simultaneously we got a species X plus. That was our target. We wanted to create E plus as X plus, and this X plus is created. Now this X plus will attack on the benzene ring like this, and the compound, that is halobenzene, will be created, and X plus will be removed from this. Next reaction is nitration. In case of nitration, my electrophile is now NO2 plus. NO2 plus is what? This is nitronium ion. Now, what is the target? We have to create this NO2 plus ion by any of the reagent. To create the nitronium ion, what we use? We use a mixture of HNO3 with H2SO4. What is the advantage of this? H2SO4 is a stronger acid, and HNO3 is a weaker acid. If it is a stronger, that is H2SO4 is a stronger, that means it will donate its H plus ion, and HNO3 will have to accept that one. H2SO4 is donating H plus to HNO3 to create a species like H2NO3 plus, right? This H2NO3 plus will release H2O, that means will eliminate this H2O molecule from itself, and we can see if I minus H2O from H2NO3 plus, I will get a species NO2 plus, which was my target to do the nit. Now this benzene ring is attacked by this nitronium ion, and we got nitrobenzene as a product by this reaction, and H plus is removed. The next reaction is Friedel-Crafts alkylation. As I am saying, alkyl group will be attacking on benzene ring. That means we have to create R plus ion. E plus should be R plus in this case. How to create? Reagent Rx with AlX3. AlX3, what is it? It is a Lewis acid. So what it will be doing? This will be taking this electron pair along with it in the form of X minus. This will create AlX4 minus, and my R plus. This is created. This R plus you can say alkyl group with the positive charge. This R plus will attack on this benzene ring to create alkyl benzene. This is many application of this reactions are there. If you want to convert benzene into toluene, you can use this. In that case, CH3Cl with AlCl3 that will be used, and my toluene will be created. Next reaction is Friedel-Crafts acylation. In case of acylation, what we are doing? We are attaching one RCO group on the benzene ring. Acyl group is what? Acyl group is RC double bond O. So I have to create RCO plus. My electrophile is now RCO plus. How to create this RCO plus? This RCO plus will be created by this type of reagent, RCOCl. In alkylation we were using RCl. Now we will be using RCOCl with AlX3. This RC double bond O plus. This species will be created by this Friedel-Crafts acylation reaction in this case, and this RC double bond O plus will attack on this benzene ring to create this type of compound. If you see its structure, this compound is containing keto group. Actually this compound is a ketone. So alkyl aryl ketones are created by Friedel-Crafts acylation. This is the application part of this Friedel-Crafts acylation. The last reaction is sulfonation. In this case, now the E plus is actually SO3, sulfur trioxide molecule. It is not a positive charge species. This is SO3 only. For this, the reagent which we use, it is concentrated H2SO4. Concentrated H2SO4 will create SO3 ion, SO3 molecule that will attack on the benzene ring to give sulfonation reaction. Now this benzene ring is attacked by SO3 and we will get SO3H, that means benzene sulfonic acid in this reaction. So these are 5 electrophilic substitution reactions which we will get repeatedly in any of the aromatic compound. Aromatic compounds gives only electrophilic substitution reaction. Electrophilic substitution reactions are given by only aromatic compound. These are so close to each other. Now let us see what will happen if we are talking about simply benzene ring or any group is present on the benzene ring in that type of compound like phenol, aniline or anything else. Look, in case of benzene, simply if it is benzene, 6 hydrogens which are actually to be substituted by electrophile, these all H are same. In that case, whatever the hydrogen you like, you can replace it with electrophile. There is no difference. This and this. There is no difference in all these hydrogens. That means when you are reacting benzene with the any of the electrophile, the same product, any hydrogen can be substituted by and same product you will get. All hydrogens are same. But if any group is present on the benzene ring, after that these hydrogens remains no longer same. Now these 5 hydrogens are not same. 1, 2, 3, 4, 5. Now these 5 hydrogens are different. Let me tell you one thing at this point. In electrophilic substitution, only hydrogen is replaced by electrophile. Never a group will be replaced by electrophile. This is a fact. Only hydrogen we have to focus about. So in this case, phenol, aniline, toluene, whatever the compound you are taking, if my functional group is directly attached on the benzene ring, in that case, if we are talking about the electrophilic substitution reaction, these 5 hydrogens are actually not same. How these are not same? These are present on 1,2 position with this group. These 2 hydrogens are called as ortho. These 2 hydrogens which are present at the 1,3 positions, these are called as meta. And this hydrogen which is present at 1,4 position is called as para. Which hydrogen will be substituted? This or this? It will be decided by this group. This group will decide, okay, this hydrogen will be substituted by the electrophile and this property of this functional group is known as directive influence of this G, that is functional group. Simultaneously, one more thing will be there. We are comparing this compound's electrophilic substitution reaction with normal benzene ring. Reaction in this type of compound will be faster or slower than benzene ring. This also will be decided by this functional group which is present on the benzene ring. And this will be called as activating or deactivating effect. If the compound is giving you the reaction faster than benzene ring, the group will be called as activating. And if it is showing the slower reaction than benzene ring, this would be called as deactivating group. Activating and deactivating effects are these. Now, let's first of all talk about the directive influence of the group present on this. To understand that part, first of all, think about one thing only. E plus, that is electrophile, attack only on negative side, right, where the heterolytic cleavage is occurring, and E plus will be attacking on the negative side only. To understand the directive influence of any of the functional group, we will have to talk about the resonating structure shown by that particular functional group with the benzene ring. This is the case 1. OH-like group. OH-like group, that means the group which are having the lone pair on the atom which is attached with this carbon. When the lone pair is attached on this lone pair will take participation in the resonance with the benzene ring like this. This lone pair is coming here, double bond is coming here. Negative charge is occurring on this position. Negative charge will come here, double bond will be going here. Negative charge on this position. Negative charge, double bond, and this type of species, right? Negative charge is here. This type of, these 3 resonating structures will be shown, and finally this structure will be resumed. So if you see all these resonating structures, you can see that negative charge is occurring on 1, 2 and 3. These 3 positions, that means 2 ortho and 1 para. That means when E plus will attack, that E plus will attack on these three position with a preference, right? Its preference would be on 2 ortho and 1 para. That would be called as, now this is type of effect will be called as my group, that means OH. Now this group would be called as ortho para directing group, because now E plus is attacking on this position, so hydrogen will be replaced from ortho and para positions only. Now this group is called as ortho para directing group. So whenever any ortho para directing group is undergoing the electrophilic substitution, for example, I have shown you the example of alkylation. OH RX with ALX3, and on ortho position or para position R group is coming, and this type of final product will be created by the reaction of phenol in electrophilic substitution reactions. In general, which type of group will be showing you the ortho para directive influence? Generally, what happens that when the lone pair is coming in resonance, that is actually, if you know about, it is actually the plus M effect. The plus M effect showing groups will be having ortho para directive influence. Plus M simultaneously, first of all, let's take the example. Plus M effect having group are OH, OR, NH2, X. X means halogen. These all are having the lone pair on this atom, and this lone pair will be taking participation in the resonance with the benzene ring, and these will be showing you ortho para directive influence. And simultaneously alkyl group is also ortho para directive. This was about ortho para directive influence. Now we will talk about the case 2. If the group present on the benzene ring is like NO2. In case of NO2, now this double bond, that is N double bond O, this will participate in the resonance with the benzene ring. Double bond is coming here, negative charge on this position. Now this is taking electrons outside the benzene ring. That means now on this position positive charge will be created. If we will go further for the resonating structure, double bond is going here, positive charge is here, double bond coming here, positive charge here, and finally this structure is resumed. So by looking at all the resonating structure, you can see that positive charge is coming on these two and this one position. That means total 3 position. That means now E plus at least can't attack on this 3 position. These 3 positions are ortho and para. Now my E plus will not attack on these position. That means which position is left? Only meta position is left for the electrophile to attack. This type of group are known as meta directing group. We can see simply if the group is having minus M effect, that group will be meta directing. Minus M effect having groups are NO2, CHO, COR, COOH. These are very common group which if these type of groups are attached on the benzene ring, and when these will be undergoing the electrophilic substitution reaction, the next group will come on the meta position. This is called as the meta directing influence. Next effect is activating or deactivating effect of the functional group. See, electrophile, that means E plus have to attack on the benzene ring. This is called as electrophilic substitution. It will replace any of the hydrogen. If E plus want to attack on the benzene ring, one simplest thing, if my functional group is making the benzene ring more electron rich, that means if the functional group is EDG, the group will be called as activating group, right? These groups are plus I and plus M group, which are called as EDG. For example, plus I, alkyl group have plus I effect, so alkyl groups are activating. Many of the functional groups have the combination of plus M and minus I effect. In that case, if the plus M effect is dominating over minus I, then the group would be called as activating group. For example, OH, OR and NH2. When these type of group are present on the benzene ring, these will make benzene ring more reactive for the electrophilic substitution. In that case, reaction will occur in very simple condition. We will not have to use the harsh conditions to complete our reactions. If the group is making benzene ring electron deficient. That means if these groups are pulling electron density from the benzene ring, that is EWG, then these groups are called as deactivating group. Which type of groups will be these? Minus I or minus M effect having group. One of the functional group, that is NO2, it is the group which is having both of the effects, minus I and minus M. That means this NO2 is called as the best EWG. NO2 group deactivates the benzene ring highly for the electrophilic substitution reaction. Simultaneously CHO, COOH and COR, these groups are having minus M effect, so these groups also deactivates the benzene ring for the electrophilic substitution reaction. When you are talking about the benzaldehyde, for example, for the electrophilic substitution reaction, you will have to use harsher conditions to complete your electrophilic substitution reaction. Now let's talk about those functional groups which are having the combination of minus I and plus M. In case, in any of the functional group, if the minus I effect dominates over plus M, then that group also becomes deactivating. Its best example is halogen. X is having minus I and plus M, and its minus I dominates over plus M effect. That means when the halogen is present on the benzene ring, it will be deactivating the benzene ring for the further electrophilic substitution. X is called as deactivating group. At this point, I would like to tell you something. When we talked about OH, OR, NH2 and X, their directive influence, these all were ortho-para-directing because these were having plus M effect. We were not concerned with their inductive effect at that time. In these OH, OR and NH2, these are activating, as in these cases plus M is dominating over minus I. Only the halogen group is like that, which is having although ortho-para-directing influence, but it is a deactivating group because its minus I effect dominates over plus M. So I hope you understood all about the electrophilic substitution reactions. Thank you so much.